In problem number 44, we're told to find the volume created by generating a region in the first quadrant between two curves rotated around the x-axis. So for starters, we can graph these functions and find the point of intersection. We can tell that they intersect at x equals 0 and x is about 1.89549. Now, with this, we can set up our integral. Let's start by identifying the axis of revolution, which is the x-axis, also known as y equals 0. And you can see that our big radius is going to be found, the region that's being rotated is this green region in between the two curves. That our big radius is going to be found by drawing a segment from the axis of revolution to the far end of the shaded region. And then by doing top minus bottom, our big radius is going to be the sine curve, 2 times the sine of x, minus the bottom, which is y equals 0. And we won't leave minus 0 in our answer. Then the little radius can be found by drawing a segment from the axis of revolution to the near end of the shaded region. And our little radius is going to be the linear graph x on top minus what's on bottom of the radius segment, which is 0. And again, we won't leave minus 0 in our answer. So we can see that our volume is going to be pi times the integral from 0 to the x-coordinate where these points intersect. On our calculator, it says 1.895 if you round to the nearest 3 decimal places. Now, we won't round when computing with our calculator, and I'll show you what we're talking about when we get there. Then we'll have the big radius function squared. So this quantity 2 times the sine of x squared minus the little radius squared. This is how we'll set up the integral. When we go to type this into our calculator, a trick we can use to get a lot more accuracy with our computations without typing in very long decimals is this. If you look carefully and you notice, when we found the point of intersection on our graph screen, we had an x-coordinate that was listed, xc and yc, x-coordinate, y-coordinate. So we'll write down our thoughts with decimals. See, our upper limit of integration is about 1.895, but we don't want to round that decimal when using computations because it could lead to rounding error. So what we did is we just typed in xc as the upper limit of integration into our calculator when integrating. Because once we find this point of intersection, this point is stored as the variable xc until we change it. So we find another xc. And this way we can get a very accurate computation. So you see the answer we get is about 6.678, which matches option letter D. Hopefully this was helpful. Thank you for watching.